The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, thanks for joining us today for Permanganate Oxidation of Cyanotoxins and the Impact of Natural Scavengers webinar with our speaker, Juliana Laszakovits with The Ohio State University. I'm Ashley Clark, Marketing Specialist for Carus Corporation. A few housekeeping items before we get started. All attendees are in listen-only mode to help cut out on any background noise. If you have questions, we encourage you to submit those throughout the presentation using the question pane in the GoToWebinar panel or email us directly. If you submit questions through GoToWebinar, we will receive a report with the question and your contact information to follow up directly after the webinar. If you're interested in receiving a PDF or recording of the presentation, please contact us. We encourage you to share the recording within your network. Here are a few ways to find us. We have listed our website and general sales and marketing email address, as well as my email address. Do you receive our email blasts for upcoming webinars, presentations, trade shows, and technical information on various solutions? If not, sign up on our website. You can find the Join Our Email list on any landing page on the right-hand side. Be sure to select the industry when signing up to ensure you receive the most targeted information for your needs. And we can't forget to mention our social media platforms. We encourage you to connect with our Carus Corporation page, as well as our team members on LinkedIn, where we are often sharing upcoming events, including webinars, industry articles or news, sharing relevant posts from other industry experts, and more. Listed here are links you can visit for upcoming webinars, and also listed is our website. At this time, I would like to take the opportunity to introduce our speaker. Juliana Laszakovits is an environmental engineering PhD candidate in Dr. Allison McKay's lab at The Ohio State University. Prior to attending The Ohio State University, Juliana attained an ACS certified Bachelor of Science degree in chemistry in May 2016 from the University of Mary Washington in Fredericksburg, Virginia. At the University of Mary Washington, she conducted research on aquatic photochemistry under the direction of Dr. Charlie Sharpless and earned departmental honors for her work. Juliana transitioned into studying permanganate as a removal strategy for cyanotoxins when she joined Dr. Allison McKay's lab. Currently, she is interested in understanding how organic compounds are transferred during drinking water treatment using mass spectrometry.
All right, so thank you for that introduction. Ashley said I'm going to be talking about how we can use permanganate oxidation to treat cyanotoxins and also account for natural scavengers that are in the water. Before I get started, I'd like to thank, I'd like to acknowledge the people that have made this work possible, and particularly my lab group, my advisor, Dr. Allison McKay, for all the support that she's given me. My lab mate, Andrea Patterson, for some of the work that she did helping to track permanganate in aquatic systems. And Dr. Carissa Hipscher, one of my former lab mates, who was kind enough to share her samples with us. I'd also like to thank Todd Hone, who's the Salina Assistant Superintendent of Water. He's been really helpful just for helping us understand the problems that treatment plant operators are facing when dealing with these harmful algal blooms, and also sending us samples, things like that. This work was supported by the Ohio Department of Higher Education and an Ohio State University fellowship. Also want to, of course, thank Carus for the opportunity to present this work to you, and the American Water Works Association for granting me permission to show some screenshots of their CyanoTOX calculator. So if you're not familiar, harmful algal blooms have been a really big problem, especially here in Ohio. So these are two images from two different sites here in Ohio. On the left is Colin Park, which is actually in Lake Erie. And so in Lake Erie, they have cyanobacteria that tend to form scums. So it's basically large chunks of cells that congeal together. They can be pretty gross. So you can see the scums kind of starting to form in that picture in the wave and whatnot. Or they may not have such a gross appearance. In Salina, in Grand Lake St. Mary's, which is the image on the right, the water mostly just looks kind of green, but those cyanobacteria don't necessarily form scums the way the cyanobacteria in Lake Erie do. And these blooms can get pretty large. So this is a satellite image from NOAA. And in the bottom left corner, you can actually see it kind of looks like land in the middle of Lake Erie, but that's actually a cyanobacterial bloom, a harmful algal bloom. And the reason that we're concerned about these blooms from a drinking water treatment standpoint is because they can produce toxins. And so in Ohio, we've seen a lot of neurotoxins, particularly in the eastern part of the state. We've seen saxitoxin. And they can also produce liver toxins, which include cylindrous spermopsin and microcystin. So microcystin is the toxin that we see most commonly here in Ohio. So a lot of work has been focused on treating microcystin. But I think it's also important to note that with the changing climate, we're more and more likely to start seeing cylindrous spermopsin in higher frequency. So cylindrous spermopsin is widely considered to be a tropical toxin. But again, as the climate continues to change, if we have warmer summers, it's more and more likely that we're going to be seeing cylindrous spermopsin in the intake of drinking water treatment plants. So the motivation behind this work, and a lot of work that's being done in Ohio, was the Toledo water crisis in 2014. So in August in 2014, Toledo had a do not drink warning issued, meaning that the level of microcystin in the finished drinking water exceeded the allowable level set by the Ohio EPA, which is 1.6 micrograms per liter for the general public. And so this left about 500,000 people without water for 3 days. When I was talking to Todd Hone at Salina, he said that you could drive an hour outside of the city and you couldn't find bottled water. So that was what prompted a lot of the research, and what honestly gave us funding was that crisis in 2014. But what I think is kind of cool about kind of one of the outcomes of that crisis was that now we're actually able to take all this information that we've been collecting here in the state of Ohio and apply it when other states are running into issues with harmful algal blooms. So for example, the city of Salem, Oregon issued a do not drink warning last summer, which lasted about 5 days because they exceeded the allowable level of toxins in their finished drinking water. And so they were able to dose in powder activated carbon in order to deal with the problem and react relatively quickly. And so the reason we know that powder activated carbon is effective is because of a lot of the work that's being done here in Ohio. So it's cool to see how it can be used in other systems in other states and even globally. So I'm going to be focusing today on permanganate oxidation, which is just one strategy that can be used to deal with these toxins. So permanganate is a black solid in the potassium salt form, which you can see on the left in that image there. And when it's dissolved in water, it forms this really nice purple color, which makes it pretty fun to work with. And then I have the chemical structure down there in the bottom right. So the reason permanganate oxidation is used in drinking water treatment is because it's an unselective oxidant, meaning that permanganate will react with with a lot of different compounds, and it's not really picky about what it will react with. So because of this, it's already approved for use by the US EPA for disinfection byproduct reduction, iron and manganese removal, as well as taste and odor control. So again, this is because it's an unselective oxidant, meaning it can react with all these things to help us remove them from drinking water. Additionally, one of the nice things about permanganate is that it's fairly inexpensive and it's easy to use. So you don't need special training in order to use it. And it means that it's more accessible for smaller treatment systems. So Smaller communities may not have access to high-tech things like ozonation, but they would have access to permanganate. So if we think about a typical drinking water treatment, you have your coagulation, flocculation, sedimentation, sand filtration, disinfection, and then finally distribution. And really out of these treatment processes, if you have toxins in your drinking water and you're pulling from a harmful algal bloom impacted water, the only strategy out of this conventional treatment that's going to possibly remove the dissolved toxins is going to be in that disinfection step. However, each treatment plan is unique, so there's different ways you can outfit it in order to deal with things like this. And so permanganate oxidation is typically applied at the beginning of drinking water treatment. And so I kind of view permanganate oxidation as our first line of defense against these cyanotoxins. And so it can be added, typically it's added at the intake, so where the water is pumped in and moves down for further treatment. And it's relatively easy to set up. So this is the setup that they have in Salina. Basically, you load the solid into a chemical feeder. You could also feed it directly as a solution. And then that solid is gradually leached out of the feeder and mixed with water. And so you can kind of see towards the bottom that nice purple solution that's characteristic of permanganate. And so then once it's in the solution form, it's really easy to dose into your drinking water treatment scheme. So if you're thinking about how you can deal with these toxins, if you're a drinking water treatment plant that hasn't had to deal with them, one of the tools that's available through the American Water Works Association is the CyanoTOX calculator. And so it's not a compliance tool, but it does help make some predictions. And when you're thinking about what you might be able to use in order to remove these cyanotoxins. So this is what the calculator input page looks like. So you would select your toxin type. So in our case, we're going to select microcystin LR. And then you input the different system parameters. So what pH is your water, what temperature is your water. We pulled a sample, it was at pH 7.6, and we brought it into the lab. So our temperature was around 25 degrees Celsius. And then you input your initial cyanotoxin concentration. So we actually spiked in microcystin LR to a sample at 56 micrograms per liter. And then you can select your target option. In this case, we've input a target cyanotoxin concentration of 1.6 micrograms per liter. And so that's an allowable level based on Ohio EPA regulations. And then of course for our oxidant type, we're going to select permanganate. And so then if we go to the CP-based calculator, because if you're thinking about this for the first time, that's probably where you're going to start, is what's your contact, based on what your contact time is. And so if we enter a contact time of about 25 minutes, what we end up with is a plot that plots basically our time versus our cyanotoxin concentration, our microcystin concentration. And the calculator predicts that the microcystin would be removed relatively quickly. However, when we did the same experiment in the lab with our water sample, we didn't see that rapid decay. We can see in this plot that the microcystin's been removed somewhat, but not fully. And we can see that that reaction's actually probably stopped around 10 minutes, which may suggest that the permanganate's been completely consumed at that point. And so again, we're comparing what our final microcystin LR concentration is after 25 minutes. We're comparing 34.5 micrograms per liter is what we measured in the lab versus 0.9 micrograms per liter is what's predicted by the CyanoTOX calculator. So that's a pretty large discrepancy. And so our question pretty much became, how can we improve the CyanoTOX calculator? How can we make this tool more useful for people? Is there a way that we can predict the degradation of these toxins in a more robust way? And so our approach to do this was to first validate toxin reactivity. So to check that the rate of reaction between permanganate and these toxins is fairly well characterized, but we just wanted to check again. So we did this for 3 different toxins: saxitoxin, cylindrospermopsin, and microcystin. And then once we had those characterized how fast those reactions happened, then we wanted to vary the water quality. So we varied alkalinity, pH, and temperature. So these are fairly typical water quality parameters that may affect how quickly permanganate is able to react with our microcystin toxins. And then after that, we wanted to quantify how much competition there is for permanganate. So there may be some naturally occurring competitors, such as cyanobacteria or dissolved organic matter, that are going to be present in that intake water. But we don't know how quickly they'll react with permanganate. So if these things are reacting with permanganate, they're not going to react with our toxin, and it's going to reduce the effectiveness of our treatment. And so instead of going through a bunch of chemical kinetics with you guys, I'm going to be presenting our results in terms of how long will it take 1 milligram per liter of permanganate to reduce the toxin from 50 micrograms per liter down to 1 microgram per liter. So I didn't mention this on the previous slide, but with saxitoxin, we actually use a few different chemical analogs to estimate how quickly saxitoxin would react with permanganate. This is because of how toxic saxitoxin is, so we didn't really want to work with it unless it seemed like permanganate would be promising to remove it. And so I have the chemical structures here. You can see how they resemble different parts of the saxitoxin molecule. But in general, what you'll notice is that microcystin could be removed from 50 micrograms per liter down to 1 microgram per liter relatively quickly on the order of minutes, whereas cylindrospermopsin and all 3 saxitoxin analogs that we use were on the order of days. So permanganate isn't going to be an effective treatment for those. And so we kind of can consider 2 hours as like a rough cutoff for what we would consider reasonable removal in these high purity conditions when there's no other competitors around. And reason I'm picking 2 hours is because the permanganate contact times can really vary from treatment plant to treatment plant. So I've been to some treatment plants where it's a relatively short contact time, around 30 minutes, but there are other treatment plants that dose in at the intake, and then the water travels for up to 8 hours before it reaches the plant. So that has a much longer contact time. But so from this first set of data, we can conclude that permanganate oxidation is only feasible for microcystin. Fortunately for us here in Ohio, microcystin is the toxin that we see most commonly, so it will at least be effective for the most common toxin that we have here. So for the duration of the presentation, I'm going to be focusing on microcystin since we pretty much ruled permanganate oxidation out for these other cyanotoxins. So then we moved on to looking at different water quality effects. So in our left bar, we have our high purity water condition, which I just presented. And then what we did was we varied the pH while keeping alkalinity constant down to pH 6 and up to pH 9. What you can see is that how long it takes to reduce the microcystin down from 50 micrograms per liter to 1 microgram per liter doesn't vary very much. So we don't see a change in how fast this reaction occurs with pH. We then kept the pH constant and bumped up the alkalinity up to pretty high, 50 millimolar. And again, we see the same thing. So there's no change with alkalinity. Now, not surprisingly, we do see a change with temperature. So the reaction goes slower at colder temperatures and faster at hotter temperatures. Typically, these blooms occur in the summer. So we actually get a little bit of a boost from the heat, helping to make that permanganate reaction happen a little bit faster. But that's something that we can account for relatively easily. So with our first steps done, we validated the toxin reactivity and saw that permanganate oxidation is really only effective for microcystin. And then we moved on to water quality and saw that alkalinity and pH really don't affect how fast that reaction between permanganate and microcystin happens, but temperature, of course, does. And so I think it's important to note that our results match pretty well what's in the literature. So that was encouraging to us to say that any issues or any discrepancies that we saw with the CyanoTOX calculator aren't due to these underlying chemical kinetics. But instead, it's more likely coming from some competition in the water, so either from cyanobacteria or dissolved organic matter. So that's what we moved on to next. And so again, I'm not going to go through the chemical kinetics. Instead, I'm going to frame our results in terms of the question, how much extra microcystin remains at 40 minutes? So that's about how long it took to reduce our microcystin from 50 micrograms per liter down to 1 microgram per liter. Now we're wondering how much extra microcystin is going to be remaining at that time. So if we look at how much microcystin is remaining on the left, again, I have, if we didn't have that bloom there, we would have about 1 microgram per liter remaining. But then we can define our bloom conditions by low, intermediate, or high. And these are kind of based on guidelines from the US EPA. So if you have about 5 micrograms chlorophyll A per liter, that's a relatively low bloom condition. If you have an intermediate bloom, you may have around 25 micrograms chlorophyll A per liter, and then a high bloom would have around 100 micrograms chlorophyll A per liter. So what we can see is that there's not a huge difference in the low and intermediate bloom conditions, but we do see more microcystin remaining under high bloom conditions. So in general, cyanobacteria are not going to be a significant source of competition, but if we are under high bloom conditions, we can account for how much the permanganate is going to be scavenged by cyanobacteria using chlorophyll A concentrations. With dissolved organic matter, though, it was a different story. So here I'm plotting how much extra microcystin was remaining at 40 minutes compared to how much total organic carbon was in the water. So that red dot on the far left is if we had our high purity conditions with no organic matter around. And basically, organic carbon is a parameter that would be readily available to treatment plant operators, and it can act to help quantify about how much dissolved organic matter is present. It's a good proxy for it. And so what we see, of course, is that as there's more organic matter present, we see more microcystin remaining. And so the reason for this is because if we think about what's happening, permanganate can react with two things. It can either react with the dissolved organic matter or it can react with microcystin. So if we have more dissolved organic matter present, then the permanganate is going to react more so with the dissolved organic matter and less so with the microcystin. And so that this competition kinetics makes sense. However, what you may notice is that there's quite a bit of variability in the data. So if we look at we had a few samples that had an organic carbon concentration of 7 milligrams per liter. And we see a lot of variability in how much microcystin remains at 40 minutes. And so that means there's some variability in how efficient the dissolved organic matter is in reacting with the permanganate. So what we wanted to do then was to have a parameter that could account for this. And so one dissolved organic matter parameter that I like is the E2A3 ratio, which is simply the absorbance at 254 nanometers divided by the absorbance at 365 nanometers. So this means it can be obtained from a simple UV-Vis scan. This is something that, again, would be readily available to treatment plant operators. And so this is what a typical dissolved organic matter absorbance spectrum looks like. And what the E2E3 ratio is doing is it's describing how quickly the absorbance tails up in the UV in the lower wavelength region. So it's that absorbance at 254 divided by absorbance at 365. And so that red line basically approximates what the E2E3 ratio is actually describing. And so the reason that the E2E3 ratio is interesting to me is because it's been shown to be correlated with electron donating capacity of dissolved organic matter. So if you have low E2E3 ratios, it's been shown that the dissolved organic matter tends to have a higher electron donating capacity, and vice versa. If you have a high E2E3 ratio, you tend to have lower electron donating capacity. And the reason we're interested in electron donating capacity is because if we think about what's underlying this process of the reaction between permanganate and dissolved organic matter. So what's happening is the dissolved organic matter is giving electrons to the permanganate. So that means that if the dissolved organic matter has more electrons to give, meaning it has a higher electron donating capacity, the dissolved organic matter is going to react more so with the permanganate. And this means the permanganate will then be less available for reaction with microcystin. And so if we plot how much extra microcystin we have and we normalize it to how much organic carbon was in our water sample, we see the trend that we would predict. So at lower E2, E3 ratios, meaning higher electron donating capacity, we see there's more microcystin remaining, meaning the dissolved organic matter reacted fairly efficiently with the permanganate, making it less available for reaction with microcystin. And at high E2, E3 ratios or low electron donating capacity, the dissolved organic matter was not as effective at scavenging the permanganate. And it's still not a perfect fit, but the E2, E3 ratios do a decent job characterizing how efficiently the dissolved organic matter competes for permanganate oxidation. And so now that we have quantified how much competition there is for permanganate, and we've shown that dissolved organic matter is a pretty significant source of competition, what we wanted to do then was build a model with this data that we had collected. So again, we have two underlying reactions. We have permanganate reacting with dissolved organic matter or cyanobacteria, our competitors, and forming some kind of product. And we can also have permanganate reacting with microcystin and going on to form the degradation product, and that's the reaction that we really want to happen. So then what we do is to build our model is we made two assumptions. First, that the concentration of dissolved organic matter isn't changing over time, and we have some other data from some total organic carbon analyses to suggest that this is a pretty decent assumption. And then second, we assume that the concentration of permanganate is much, much bigger than the concentration of microcystin in our water sample. And so for most points in the reaction, this is going to be true. So again, it's another good assumption we can make. So then if you do a bunch of fancy math and some derivatives and integrals and all that good stuff, what you end up with is a function that describes the change in microcystin as a function of time. That's based on how much microcystin was initially there, how much permanganate did you add, the rate of reaction between microcystin and permanganate, and so that's what we determined in part 1 of our study, and then the rate of reaction between permanganate and the scavengers or the competitors, that dissolved organic matter, cyanobacteria that's present. And so that was what we determined in part 2, was that rate of reaction between our competitors and our permanganate is a function of how much organic carbon is there, so how much organic matter is present, the E2, E3 ratio, which is a measure of how efficiently the organic matter can scavenge permanganate, and then also chlorophyll A concentrations if we want to take into account cyanobacteria, which will be more important at high bloom conditions. And so then we went out and got more water samples. We didn't filter these, we just took them back to the lab as they were. So what we did was we compared what our model would predict, which is the black line labeled competition in this plot. We compared it with what the CyanoTOX calculator predicts, which is the blue dotted line down at the bottom. And then we also measured what the actual removal of microcystin LR was in these samples. So the first sample we had was from Stone Lab, which is a laboratory that's owned by Ohio State up in Lake Erie. And so this was early in the bloom season, so the bloom hadn't actually made it to Stone Lab yet that year. So because of that, the chlorophyll A is relatively low at 2 micrograms per liter. The total organic carbon is also pretty low, around 4. And then the E2, E3 ratio is fairly high at 6.9. And so what we see is that we see pretty good agreement between our model and what we actually measured in terms of microcystin removal. So comparing the percent difference, that's the 40 at the last time point. We're off by about 25%, whereas the CyanoTOX calculator would be off by around 80% if you just use the CT measurements. Then we also grabbed a sample that was basically at the beginning of the bloom. So this is from Colin Park, also up in Lake Erie. And this was for when the bloom was starting to pick up. So it hadn't gotten in full swing yet. It was still, the bloom was still building at this point in the summer when we pulled the sample. So the chlorophyll A is a little bit higher. The TOC is also a little bit higher, but the E2, E3 ratio is a little lower. And while we don't see perfect agreement between our results and what we actually measured, we see much better agreement. So the percent difference is about 19% as opposed to 86%, which is what the CyanoTOX calculator would predict. And then, of course, we pulled the sample from a high bloom condition. So Buckeye Lake is a lake that's east of us here in Columbus. And in the summers, it has really bad cyanobacterial bloom. So the sample was pulled kind of in the heat of that bloom. So the chlorophyll A concentration was really high, 160 micrograms per liter. The total organic carbon was also pretty high, 7 milligrams carbon per liter, and the E2, E3 ratio was comparable to that previous sample. And again, we see much better agreement between our model and what we actually measured in terms of how quickly the microcystin decays. So we're seeing a percent difference of around 17 as opposed to 84 for the CyanoTOX calculator. And so it's great that we can predict this, but it's also important to think about what can we do when the competition from dissolved organic matter is significant. So if you're treating the water from Buckeye Lake, you still need to be able to remove that toxin. And clearly that's not going to happen very effectively if this is your removal that you're seeing. So one of the things that we stumbled upon is we've been doing some work to understand how permanganate oxidation actually alters dissolved organic matter. And this was actually just submitted yesterday as a manuscript, so hopefully that'll be coming out soon. But so if we think about our dissolved organic matter, it's undergoing reactions with permanganate and it's forming some kind of oxidized dissolved organic matter that the composition of which is going to be very different than the initial dissolved organic matter that entered the treatment train. So in particular, what we've seen is that the E2, E3 ratio tends to increase when after permanganate oxidation. And what this means is that you have a decrease in electron donating capacity, meaning that this dissolved organic matter now will be less reactive with potassium permanganate than it was when it first entered the plant. And so what this means you can do, so if you have your initial dose of permanganate, you may get some sort of decay like this, but you still see a lot of competition from your dissolved organic matter. If you then add a second dose, if the organic matter's composition hadn't changed, what we would predict is this removal. So it's only getting down to around 20 micrograms per liter, which still isn't close to what we want. But because the dissolved organic matter composition has changed, what we see is we actually get a boost by adding that second dose. And so we see much better removal when we add a second dose of permanganate after the dissolved organic matter has been allowed to react with permanganate for a little bit. And so thinking about what this would mean for an actual treatment plant operation, if you could basically add in a second dose somewhere along the treatment train, you could actually get a boost in your toxin removal without increasing your concentration of permanganate very much. So a lot of treatment plants dose permanganate at the intake of treatment. You could still have your first initial dose there and then have a second dose basically when the water gets back to the treatment plant. And then you'd basically get this boost from the fact that the composition of the dissolved organic matter has changed as it's moved to the treatment plant. So with that, I'm going to wrap up with some conclusions. First, I think I've shown that dissolved organic matter efficiently competes with competes with microcystin for permanganate oxidation, meaning that permanganate oxidation is going to be less effective at removing microcystin. But we're able to account for this competition using total organic carbon measurements and the E2A3 ratio. Both of these parameters would be readily available to a treatment plant operator. And then finally, we've also shown that sequential permanganate additions can improve microcystin removal. So if you have any questions that don't get answered during the Q&A period, please feel free to reach out to me. My email is down at the bottom there. Or if you're like the work that was presented here, you want to read more about it, these results have been published in Water Research earlier this year. So thanks for your time. I'm happy to take any questions now.
Thank you, Juliana. We do actually have a few questions that came in. The first one is, do you know what dissolved organic matter compounds are reacting with permanganate?
So that is something that we've been looking at. So I've been using mass spectrometry to try and answer that question. And the compounds that I think are most likely reacting with the permanganate are compounds that contain alkyl benzene groups. So permanganate can react with the carbon hydrogen bond that's next to the aromatic ring to cleave whatever's added on to that molecule. So I think that's one main source of competition. And then the other one that we've been identifying is nitrogen containing aromatic compounds. So if you have like a amine group that is next to the ring, it can actually activate that aromatic ring, basically making it more attractive for permanganate to react with it. And so that's the other big source of competition that we think we're seeing from dissolved organic matter.
Okay, thank you. The next question that has came in is, the CyanoTOX calculator seems fairly inaccurate. Should it still be used or can it be fixed?
So I think it would be great to incorporate basically total organic carbon measurements and E2A3 ratios or SUVA 254 values. And I think it would be a relatively easy fix to add these to the calculator to make it a little bit more accurate and make it a better predictive tool. The calculator also has a second way of predicting the decay, but the issue is that you need to know how quickly the oxidant is being consumed by your water. So that's another way that you could account for that competition. But one of the issues that our group has been running into is the fact that the ways we measure permanganate in water are really susceptible to interference by other organic compounds. So we don't necessarily always get an accurate measurement of the permanganate concentration in the water. So that still could lead to some inaccuracies there.
Okay, and the last question is, in regards to the sequential permanganate dosing, what would happen if you added the second permanganate dose earlier or later?
So I suspect that we would see similar removal. I don't think necessarily like the time of addition would matter too much, but I actually just started doing some work. There's an undergraduate student who's working in our lab who is going to be digging into that question a little bit more. So hopefully in the future, we'll be able to say definitively how that timing would impact the microcystin removal.
Perfect. And I think that's all the questions for now. So thank you again, Juliana, and thank you everyone who tuned in to watch. Have a great day.